So what do you think about Trump and his, is that for a while?
I just think that's like the scariest thing in the world.
Well, you know, things happen, you know, I look back at people that had to do internments in Japan, Chinese people that for China, I mean not China, but for Japan, and the executive order, you know, that's just so in reality, history does repeat itself.
True. Yeah, hopefully we won't come to that. But
No, it won't.
it's scary.
We won't intern people. I hope not.
Yeah, correct.
Oh Lord.
Yeah, I'm there with you.
But you know, I understand. I mean, I'm sure that there's a lot that has to be done. Unfortunately, you know, like today,
Hey.
they mentioned about the tech companies and they're like up. They're like on fire. So what they did is they're dumping money in it. They're dumping like 100 million into these ACLUs and all these places, and they're like giving them money so their tech people won't be missed.
It's true though. Yeah. I mean, there was a sort of a Google engineer who was on location in London, and then he was supposed to be there all week. They didn't let him in. They sent him back. I don't know.
I don't know.
I understand that there's a fear that someone might have bad intentions.
Well, you know, we have that now.
Punish a whole population for a fear that a small minority.
I know, but what do we do?
Yeah.
How do you change the nightmare?
Yeah.
I don't know.
For sure. Talk about a gift to like radical terrorists anywhere. America won't even make Muslims. That's an easy thing to sell.
Yeah. It's pretty wild.
How's it going there? How's it going?
Yeah.
Oh, yeah? Oh, my God. What's it called? On the New Year? Okay. Did you wear red? Or is that only okay. Got it. Yeah. Happy Chinese New Year. Happy Lunar New Year.
That wasn't intended to be a hard question. Did you have a good weekend? I'm glad it's not raining anymore.
Oh, yeah.
So what I want to talk today is inversion method for random number generation. And why do we care about this? So we've seen the abstract case several times at this point, but we still haven't actually finished it. And to finish it, we need to know how to generate numbers from something that's not a uniform distribution. So we need to know a triangular distribution in particular. So where we're heading for is how do we generate samples from a triangular distribution? And in order to answer that question, I'm going to give you a general method for generating samples from, I'm not going to say any, but almost any continuous distribution. So the way the class is going to go is I'm first going to talk about the normal distribution. So this is going to be an excuse for me to introduce you to a couple more common continuous distributions. And we're going to talk about how to generate samples from each of these different distributions. And then at the end of class, I'm going to let you finish the abstract case. And where the last class went was we didn't have quite enough time to finish it. We just kind of got to starting to think about how do we generate samples from the triangular. So we'll just see how that goes and see how much time things take. Okay, so let's sort of start with the normal. normal. So I'm guessing that this is a pretty familiar distribution. It's a continuous distribution. It's probably one of the most popular continuous distributions. And you have a random variable. It's got some mean. It's got some standard deviation. Mu is a common Greek letter for mean. And what is mu? Mu is, well, normal is this bell-shaped curve that you see a lot. Mu is exactly at the peak of this bell-shaped curve, and that's the mean of the distribution. That's the mean of the normal distribution. The sigma over here, the standard deviation, is controlling the spread. So if you look at the spread, if I look at what this thing is doing, I'm probably seeing a lot of values between like 7 and 13. If sigma was larger, I would be seeing values between maybe like 4 and 16, okay? Okay, so sigma is controlling the range of values that I'm seeing. If I say standard normal has mean 0 and variance 1. So standard normal looks like this. And how do I deal with the normal in Excel? So it turns out that understanding this is very closely related to this inversion method. So we can do it for the normal distribution. I claim we've got the general idea for how to do it for any distribution, albeit the fact that we'll have to do a little bit more algebra. So I'm going to belabor how we do things, not belabor, but I want to go really slowly over how we do things for the normal distribution because I want to make sure all of you have the connection between what I'm asking for normal, how I generate it in Excel, how I get the CDF, the PDF, the inverse, all of these different things. So first of all, if I have a normal random variable and I want the CDF, this capital F, this is asking me for the probability that the normal random variable comes back less than some z. And the command in Excel is norm.dist. And mu and sigma are controlling the mean and standard deviation. So if I have this z equal to mu, equal to the mean, what is f of mu going to come back as? 50, right, 0.5. Why? Because if you look at this picture here, 50% of the values are on this side of the curve, and 50% of the values are over here on this side of 0, and 0 is the mean. And that's exactly true here, okay? So if the mean's 10, 50% of the values are on one side of it, 50% of the values are on the other side. Okay, so that's true for normal.
Is mu just for population?
Mu is the mean, so it's a common Greek symbol to use for mean. In this case, I mean that this is the mean of the distribution. This is the expected value of z. This is the average. If you have a sample of data from this distribution and you do the Excel function average, it should be coming back something close to this.
Right, so how is mu different than x bar?
Okay, so mu is, x bar is, if I have a sample from the distribution, x bar is usually the code to say I'm taking the average in Excel of a specific set of data that's a sample from the distribution. The mu is, this is the absolute truth. The mu is what x bar is trying to estimate. The mu is God's truth. That's what the statistician would say. So your x bar is basically estimating mu. Mu is absolutely exact. Okay, and so the two differences here is this capital F is always going to return you a probability, something between 0 and 1. This F is returning you the height of the PDF. So the F is giving you a value on this, the actual value on this curve. The capital F is giving you the area under the curve. So I think this is actually useful to do in pictures. So this idea of the difference between the PDF and the CDF is central to continuous distributions. And before I do that, I'm going to do everything for a standard normal. And why am I going to do things for a standard normal? So first of all, if I have a standard normal, you can do a norm.s.dist, and the norm.s is telling Excel it's a standard normal, so you don't have to enter in the mean and the standard deviation. And secondly, so if I have a standard normal and I add 10 to it, what what's going to happen? Yeah, it's going to translate the curve on the axis. So if I have this standard normal and I add 10, I'm going to get that picture. So I can get from a standard normal to any normal that I want by adding something, and the way I change this spread is I divide by something, or I multiply by something. Divide or multiply. Okay, so that's nice. So if I do things for a standard normal, you're getting the sort of bright idea for any kind of normal. And now, my artistic skills aren't great, but I want to go between my artistic skills and our Excel commands. So here's a standard normal. And this is the PDF for the standard normal. So this is my normal PDF. And I'll call this is Z, so this is f of Z. And for a standard normal PDF, this is 1 over square root of 2 pi e to the negative Z squared divided by 2. And how do I get the PDF values? Well, let's go to our laptops for a second. And if you can just open up an Excel sheet. I know this is freehand, I just need you to have an Excel open. And if I type equals norm.s.dist of 0, comma, cumulative toggles on 0 or 1. So if I want the cumulative, I write a 1. If I want the PDF, I write a 0. I've graphed right here the PDF. So if I want the value of f of 0, this equals norm.s.dist of 0, comma, 0, because 0 is telling me PDF. So 0. And that is like 0.4. Why isn't that 0.5? So what's the difference? So let me do something else. So now type equals norm.s.dist of 0, comma 1. And I get 0.5. So can somebody explain to me the difference between why if I do comma 1 I'm getting a 0.5 and if I do comma 0 I'm getting 0.4?
Because when you're doing the 0, you're not asking what the probability that it's 0 or less, which would be half. That's like filling up half. You can see it graphically. You're asking what the height of the graph is right there, and it's not 50%.
Yeah, so okay, so this is exactly it, and I think this is an important difference to keep in mind. We talked about it last Wednesday, but it's good to see it here. So if I ask for capital F of 0, capital F of 0 is my probability the normal is less than or equal to 0. Capital F of 0 is my norm.s.dist of 0, comma 1. And I've colored in this part because it's the area under the curve. So I said something about probabilities being interpreted as areas under the curve. Well, this is exactly what Excel is calculating for you. When you say norm.s.dist and you put a 1 in there, Excel is calculating for you the area under the curve. In this case, it's calculating the area under the curve up to 0. When I ask for norm.s.dist and I have a 0 there, I'm not calculating the area under the curve, I'm just calculating the height of that PDF. And how do I interpret this value f of 0? This value f of 0 is 0.4. How should I think of that value 0.4? It's not the probability I get a value less than 0, so how should I think about it? Okay, so it's the value of the function at y equals 0, but I want a probabilistic interpretation. Is it the probability that the standard normal equals 0? But that has something to do with it. So it's you can think of it as the probability it returns something close to 0. Okay? So if we look at this PDF, you could think of the PDF as the probability, my standard normal, which I'll denote by a z, is say between negative 0.01 less than z less than 0.01. If I want to get that as an approximation, it's this little f of 0. So it's this value, it's this 0.4, times the length of this very small interval, which is like 0.02. Okay? So you can interpret the PDF as being the probability you get a value around 0 in a little interval. We know the probability of exactly 0 is 0. You're interpreting the CDF as the probability that you get a value less than or equal to 0. Okay, so next thing, I can graph both of these things. I can graph the PDF and I can graph the CDF. So this PDF for the normal is looking like this bell-shaped curve. This CDF for the normal, what should the CDF for the normal look like if I want to graph that curve? Yeah, Alex.
Yeah.
You did this exactly. You gave me this little S with your finger. Yeah, right? So the CDF is looking something like this. So this is a Z, this is an F of Z. And this is corresponding to the area under the curve as I move Z in this direction. Okay, so what is capital F of 0? Right? Because I'm just asking for the probability I'm less than or equal to 0. And now this is where, this is the important thing to sort of get at. If I ask you for let's say this is negative 1.5, right? If I ask you for capital F of negative 1.5, right? What is that in Excel? Capital F of negative 1.5 is equals norm.s.dist of negative 1.5, and I want the cumulative, so it's a 1. So this is norm.s.dist of negative 1.5. I want the cumulative, so I'm putting a 1 in there. And that is 0.066807. Now, if I go back to my podium for a second, I said something about, what if you want to know the value of z such that the probability we're less than or equal to a little z is some p for a given probability? So that's this norm dot inverse. So now let's go back to Excel. And let's type into Excel equals norm.s.inverse of 0.066807. What is that going to be? Negative 1.5. Okay? So this norm.s.inverse is the inverse of the norm.s.dist. And the picture you're thinking about in your head. This, for what we're going to do, this picture is the important thing to have in your head. This guy, on the y-axis are probabilities, so it's always between 0 and 1. So if I ask for 0.066807, what am I doing? Well, this is the probability on the y-axis, and I'm coming over here, and I'm saying, what is the z value? What is the z value that corresponds to that probability? And we've just seen that it's negative 1.5. It is equivalently norm.s.inverse of negative 1.5. And if I think about this picture on the bell-shaped curve, I'm getting the integral of the area under this curve up to negative 1.5. So what's our takeaway here? If you want to map from a probability value, something between 0 and 1, to a sample, an observation from this normal distribution, you're using this norm dot S dot inverse. Okay, and I'm gonna skip the practice questions I had on my podium because I think I've kind of done enough. Are we good with norm dot S dot inverse and norm dot S dot dist?
I think you wrote in your notes the wrong argument.
That's possible.
You wrote 1.5 for norm dot S dot inverse.
Oh, and I need another one. You're absolutely, yeah, you're totally right.
Wouldn't it be the point?
Yes. 0.0668807, and this should equal negative 1.5. Thank you.
How did you get the norm dot S dot dist 0, 0, y is 0.39?
So the norm dot S dot 0, 0, this 0 is toggling between if I want the value of this curve or the value of this curve. The value of this curve is the PDF. It's like when you do the histogram and you have all these different bins, it's like the height of one of those bins.
Okay.
When I do the 1, I'm asking for the area under this curve. When I ask for the area under this curve, it has to be between 0 and 1 if it's a well-defined PDF. And equivalently, the area under this curve could also be thought of as a function whose taking values between 0 and 1 and looks a little bit like this S shape.
Yeah.
And so this is tracking the area under this curve.
Okay.
So 1 is giving me a probability value, and in particular it's giving me a cumulative probability that's less than or equal to, so the probability I'm less than or equal to a particular value. 0 is giving me, this is the height of the function, and to get the probability I need to go between the height of the function, so this is like f of 0, the value of the function at 0,
Okay.
times a little interval around that value.
Yeah, that's like the part I don't get, right? So if that's like arbitrarily small, should it be 0? That would essentially multiply. By
Yeah,
0.
so what's the probability a continuous random variable takes on one particular value?
0, right?
It is, exactly.
So why isn't it getting like closer to 0 instead of 0.4?
It is getting closer to 0 because the smaller I take this, if I take this small, 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 that's going down to 0.
Okay.
So so what I haven't done is sort of the calculus to show you exactly what's going on here. But if I took a limit as the size of this thing gets small, epsilon, it's going to go down to 0. And if you think about what the integral is doing, it's a Riemann sum approximation.
Yeah.
And that Riemann sum approximation is actually taking, to calculate that area under the curve, the f of 0 times a little slice.
Yeah.
And I could think of this little slice in a Riemann sum approximation as being the area under a curve that's very close to 0. So that's really what I'm doing.
Okay.
And I'm really just trying to give you a probabilistic interpretation for that PDF.
Okay.
Does that help?
Yeah.
Okay.
So in layman's terms, you're saying if something's 1.5 standard deviations away, you got a 6.68% chance of that happening? Or, I'm like trying to like.
And so, okay, so let me, 6.68, this is 6.68%. You have a 6.68% chance of an observation from a normal distribution returning less than negative 1.5. This is less than negative 1.5. When I'm multiplying by the height of the PDF, I'm asking for the probability I'm returning a value close to 0. So the reason I was trying to do this mapping, if you like the calculus part of it, then that's good. If you don't like the calculus part of it, the intuition that you want to understand is that higher values of the PDF, observations that correspond to higher values of the PDF are more likely to be seen. So if you take this normal, this PDF is high around 0, you're more likely to see values around 0 than out here around 3 or negative 3. That's the important thing to take home. So somehow the probability of values that are close to peaks in this PDF is much more likely than, yeah. Okay, so this thing about the CDF, why is this important? Because ultimately, if we want to solve this case, we need to know how do I go from this uniform rand in Excel to a triangular distribution. And as a baby step here, I'm saying, well, let's just think about how do I go from rand to a normal distribution. And why am I talking, we just talked for 20 minutes over this like curve and PDF and CDF and what does the CDF mean? And so this is really the crux of the entire class, I think, right here, is when I return rand. Rand is a value between 0 and 1. So I could think about rand returning some value between 0 and 1, and I could think about it as being a value on this y-axis when I'm graphing this CDF. So if I want a sample from the normal distribution, what do I need to, one way of doing that is I'm going to say, well, what value does that correspond to on the x-axis? So I'm going to take my uniform, and I'm going to say, I'm going to look at the inverse of that value. That's why it's called the inversion method. And that just says, what x value will give me this probability? So that's the norm.s.inverse function. What I'm doing right here is the norm.s.inverse function. And I can do this. And if I keep doing this, I should be producing samples from a normal distribution. So I'm taking rand, which is giving me stuff uniformly distributed between 0 and 1, and I'm mapping rand to values on the x-axis, which is giving me samples from this normal distribution. So let's do this in our Excel file. So suppose we continue. Let's do it in our Excel file. Let's convince ourselves that I've really given you a way to give yourself samples from a normal distribution. And I've written down the steps here, and I thought it was easiest for us to just do it together. And remember, why am I emphasizing this? Because to solve this case, we got to know how to go from uniforms to giving samples for our triangular distribution. Okay, so let's do it normal first. So in B, the thing you're always going to start with is random samples between 0 and 1. So this is just rand. So in column B, I'm right here. Let's do equals rand. And then I'm going to copy rand down. I'm generating 1,000 samples. So there's 1,000 samples between 0 and 1. How am I going to go from that to the standard normal? Well, that's in column C2. We just all agreed that if I want to map from that y-axis to a sample of that x-axis, that standard normal, it's the inverse function. It's norm.s.inverse. So this guy is equals norm.s.inverse of the probability value. And I can interpret rand as a probability value. Rand is always between 0 and 1. So here's C2. So let's do this and then copy down. And I'm going to do a histogram plot, and I'm going to do another method for a histogram plot because I want my plot to be able to change with the samples. So notice that every time you press F9, you're getting new numbers in columns B and C. And that's getting new numbers because Excel's just giving you another sample from these rands. Good? Okay, so I want to produce a histogram plot that is going to change every time I get a new sample. Okay, so there's a little bit of magic. So I want to highlight cells G2 through G16. And then I want to type in here equals frequency. And then I want to highlight my data, which is column C. And then I want to highlight the bins, which is E. So I'll explain why I did column F in a second. So think of the bins as column E. And then I want to type, this is the magic, make sure you type Shift Control Enter I need them all together. So Shift, Control, Enter. On the Mac, it is Shift, Command, Enter, I think. But I'll let Mac users correct me there. And note,
It's control on that.
it's Control, okay. Control, Command, Enter.
Control shift enter.
Command Shift Enter works too.
Okay.
Multiple options. And notice if you press F9 a few times, the frequency is changing. So, and what is this frequency function? This is exactly the same thing that Excel's histogram function is doing. So this first one here is counting the number of observations I see less than or equal to negative 3.25. The second one is counting the number of observations I see between negative 3.25 and negative 2.75. The next one is counting the number of observations I see between negative 2.75 and negative 2.5. Why do I have column F? Because for my graphing, it's kind of nice to have a number that's right in the middle of these bits. That's all. Okay, so are we good with getting the frequency function? Okay, so now I just want to graph it. So I'm going to do a scatter plot. It's going to be a column. So I'm going to insert charts. I'm going to go to a scatter chart, and I kind of like it as column. You don't have to do it as column, but I like it as column, so I'm going to do column. And let's do histogram. And this is the point of what we just did, is how does that look? Kind of looks like a normal distribution. Kind of looks like a bell-shaped curve. So this is my way of convincing you, of constructively convincing you, that this method kind of works. You know, we were generating numbers that were between 0 and 1, equally likely to be anywhere between 0 and 1. And that's definitely not equally likely to be anywhere between 0 and 1. We mapped those to a different distribution of interest. Our distribution of interest was this normal distribution. That's what we got. Did I get lucky? Did I just happen to get a good sample? Well, press F9 a few times, and you can notice that your histogram changes a little bit, but the overall shape of that bell-shaped curve is pretty steady. Is it good? Good. Okay, so this is your inversion method. So I would actually claim that you're in good shape to do the triangular distribution now, or we're going to do it in a little bit more baby step. But let's think about what we did and why this works. So if you think about what I did in the first two things, RAND is giving me something on this y-axis. And then I'm converting from the y-axis to a sample of this normal. And I'm doing that a lot. So here's my little visual animated motion picture. And one thing that you can notice is, am I ever going to return a value that's like negative 10? No, not really. And am I ever going to return a value that's like 10? Not really, because down here this CDF is really close to 0, and up here it's really close to 1. And in particular, the values you're returning are clustering around the points that this slope is the steepest. Where is this slope going to be the steepest for a normal 0, 1 distribution?
0.5.
Around 0.5? 0. So unfortunately, I should have graphed the normal 0, 1. I didn't graph the normal 0, 1. If this was a normal 0, 1, this peak would be about 0. Okay? But the steepest part of the slope is exactly where this PDF is the highest. So in the picture I'm giving you, we've got a normal, and it looks like the mean's about 2. So I'm going to be giving you a lot of values around 2. But this is why it works. Because when I map from the uniform down to the x-axis, the values I'm mapping the most often that come back to me are exactly where this PDF is the highest. And the PDF being the highest is telling me that if I take observations from this distribution, these are the values I expect to see the most often. Is that good? Okay, so that's why this is working. And this gives you an algorithm to generate whatever continuous distribution you want, which is, in your column B, you're gonna generate something that's uniform. And in your column C, you're gonna map back to the x-axis, or in technical terms, I'm gonna return the inverse of the CDF function. So if I'm generating samples from the normal, I'm using norm.inverse. Okay, so let's do this for another x distribution. So right now, the thing that I have in the background is Excel does this for us, right? Excel has this norm.inverse function. The thing that gets a little bit harder is what if we have to figure out the inverse ourselves? The idea is exactly the same, it's just that now we have to solve for the inverse instead of Excel doing it for us. But the method is exactly the same. And so this also gives me an excuse to introduce another continuous distribution that comes up quite a bit. It's the exponential distribution. So what is the exponential distribution? The exponential distribution, the PDF looks something like this. So it's always, it's highest around 0, and then it decays. And it's often parameterized by something called lambda. Lambda is determining a mean. So 1 over lambda is actually the mean of the distribution. 1 over lambda squared is the variance. And this is saying that I can say, okay, so if lambda equals 1, I have an exponential distribution. Its mean is 1. It's this kind of violet curve there. If lambda is higher, so if lambda is 1.5, that means the mean is lower, 1 over 1.5, so that's like 2/3. That means I'm more likely to get values close to 0 than I am here. And on the other hand, if the lambda is 0.5, the mean is 2, so that means I'm more likely to get values out over by 2 than I am for sort of this blue curve. Why do I care about exponentials? They're often used to model interarrival times. One of the first times they came up, if you want a little bit of history, was AT&T was working on the phone networks, and way back in the 1900s, he picked up the phone, and I'm talking about the landline, not the mobiles. I'm old enough to have used landlines at some point in my life. There was a genuine chance that you might not be able to get a line, because AT&T had to calculate, well, how many lines and how much trunk space do I need? So to make that calculation, what do they need to know? How often are people calling? So if Balaji's going to call his friend, and Garrett's going to call his friend, I need to know, is Garrett going to call his friend a second after Balaji, or a millisecond after Balaji, or 10 seconds? Because that interarrival time between calls is exactly what I need to determine the capacity of the network. Turns out it's not just the distribution that was important back in the early 1900s. People also done measurements on internet connections. How often are people connecting to connecting to a web server and making requests? Turns out that interarrival distribution has often empirically been shown very often to be exponential. Okay, so the distribution comes up a fair bit. Oh, it also comes up in call centers. If you look at how often people are calling call centers, and you look at the time between calls to a call center, so you need to know that because you're thinking about how many agents to staff your call center, this distribution comes up. Okay, so that's its basic interpretation. And so we want to be able to, we want to be able to generate it. So how am I going to generate it? I actually thought I had a slide. Oh yeah. Okay. So how am I going to generate it? So let's go to my laptop for a second. And the first thing, the way you always start out, is just rand. So that's good. So in column B, I'm going to do rand equals rand. And let's give myself 1,000 samples of this exponential. Now, what am I going to do in column C? So I'm going to go on the .cam for a second over here. It might help you to get the slides on in your laptop. And let's think about this. For an exponential, it starts at 0. So this is what its CDF should look like, something like this. I've done this for you. So it's equivalent if I give you CDF or PDF. If you're comfortable with calculus, you can notice this is the derivative of this one, and this is the integral of this one. Otherwise, you can take me at my word. Oh, I should also. Because up here, you can take me at my word that this is derivative of this one, this is integral of this one, and how am I interpreting this? This is the probability that I see a value less than or equal to x. So the important thing here is for this distribution, this is giving me the probability I see a value less than or equal to x. So what am I graphing over here on my dot cam? I'm graphing this f of x, which I am told is 1 minus e to the negative x. Let's take lambda equal to 1. Okay, so I have a mean of 1. Now when I just did this uniform sample in my column B, what am I doing? One of those uniform samples is something like this. So this is u equals rand on my y-axis. I want to generate samples from an exponential. So same thing with the normal. I need to come over here and I see, okay, so if I get a u, whatever, maybe it's 0.9202, that's what I got as my first one. What does that map to down here on the x-axis? How do I solve that? Well, I know this f is 1 minus e to the negative x, so I know that 1 minus e to the negative x had better have given me u, right? I'm just plotting the curve. We good with that? Okay, so I can solve. So 1 minus u had better equal e to the negative x. So if I take a natural log, log of 1 minus u had better equal negative x, or negative log of 1 minus u had better equal x. And at this point, I'm going to make an observation. If you want things to be a little bit simpler, if this makes sense to you, excellent. If it doesn't, just keep going with this one. What's 1 minus a uniform? It's uniform, right? Uniform is equally likely to be between 0 and 1. By symmetry, if I do 1 minus u, it had better again be equally likely to be between 0 and 1. So with that observation, I could actually say, oh, you know, this guy is the same thing as saying u equals e to the negative x, which tells me that ln of u equals x. So you can use either one. They'll both give you the same thing. What does this mean for our Excel file? For our Excel file, we now know what to put in column C. I've given you the u. Column C is my x values. So column C is column B is the u. Column C is mapping from u to x. And we just got it. X is negative ln u. Okay, so over here I'm going to say equals negative ln. What's the u? It's the uniform sample. And now I'm going to copy and paste. And now you can do a histogram plot to sort of check yourself. So if I want to do, I'll use the frequency function again. Plot this. Okay, and that's pretty great because your chart is looking exactly like that exponential PDF. And you can press F9 a few times and say, oh, that's good. So that changes a little bit with my sample, but that shape is remaining very constant. That's your exponential shape. Is this good? Okay, so where are we? At this point, if I give you a continuous distribution, you know how to go from a uniform RAND in Excel to samples from that distribution. And that's great because it lets you calculate summary statistics like means or standard deviations. Or like for the case, if you can produce triangular observations instead of uniform observations, you can get at the expected value of that RFP bidlet. And that's what we're building up to, which is, now it's time for you to finish things out. Well, in about 5 minutes, I'm going to talk a little bit. So to finish this case, we need to generate samples from the triangular distribution. Okay, so what is the triangular distribution? I've given you the CDF here. This is a CDF of triangular. So if you think about what we just did on the dot cam, the f of x no longer equals 1 minus e to the negative x. It equals that thing. And I want to know what is the expected present value of the RFP alternative. And so here's your CDF. I want you to go from uniform, so you're going to start with uniform. You're going to go from the uniform, the RAND 01, generating values off of this CDF. And that's basically my question. I've thrown you a little bit of a loop because notice that this CDF is defined as one thing if we're between A and B and another thing if we're between B and C. And I think to make sure everybody starts on the same page with exactly the same CDF, let me just write out what this is. So my f of x, right, it's 0 if x is less than or equal to 3.2. What does that mean? You are not going to see a value less than 3.2. 3.2 is the minimum value you can possibly see. What about if x is between 3.2 and 5.6? If x is between 3.2 and 5.6, I'm using this guy, which is x minus 3.2 squared divided by, so this is b minus a, 5.6 minus 3.2, times c minus a, and I did that, so that's 23.04. Feel free to check me. If x is between 5.6 and 12.8, I'm using this guy. C is 12.8, so I have 1 minus 12.8 minus x squared divided by, this is 69.12, and it's 1 if x is greater than 12.8. So what does that mean? So CDFs are always between 0 and 1. They're giving you probabilities. Your x-axis, I said you never see a value less than 3.2. So it's only at 3.2 that this thing kicks in. And this is kind of a bowl-shaped parabola. And this happens up until 5.6. And what happens at 5.6? Well, at f of 5.6, if I use this guy, it's 5.6 minus 3.2 squared divided by 23.04, and that is going to give me, I didn't actually write out the value. The point I wanted to make is that this guy is exactly equal to this guy. So 1 minus 12.8 minus 5.6 squared divided by 69.12. If you do that, you'll convince yourself it's exactly the same thing. Why is that nice? Because for my graphing purposes, so that means everything's connected. And at 5.6, I start using this different guy. And it does something like this. And it reaches 1 at 12.8. And what's probably of interest to you is, so there's this value you can compute, f of 5.6, right? And your uniform might return here, And if your uniform returns here, you're going to be mapping down to this part of the axis, and you need to solve u equals x minus 3.2 squared divided by 23.04. And your u might also return up there. And if it returns up there, well, you're mapping down to this part of the axis, and you're going to need to solve u equals 1 minus 12.8 minus x squared divided by 69.12. So that's how you're going to map from your rand to your x value. This was a little bit to absorb. So the next, yeah, so I get this, but this is, I'm forcing you to think, just I'm pushing you, okay? I'm aware that I'm pushing you a little bit. But I would also say that I felt like everybody understood the norm dot inverse example. Is that fair? So if you understand norm dot inverse, the only thing that's happening here, you're doing the exact same thing as norm dot inverse, but I'm forcing you to do the algebra. I'm not letting Excel do it for you. And remember, when you looked at Excel and you went to data analysis, random number generation, it wasn't generating triangles. So this way you have a method to whatever continuous distribution is of interest to you, you can generate samples from. Okay, so now I think definitely feel free to talk to each other. I noticed in the last class that some people, there were kind of all mixes of where people were, so if you feel pretty comfortable, please talk to your neighbor and help them. Definitely talk to each other. I want you to produce samples from this triangular, which I have not quite told you, I've just gotten you started out. Once you can produce samples from this triangular, go back to our case, right? The case that I posted on Wednesday, we were producing samples of the savings distribution from uniform. So instead of producing samples from the savings distribution from uniform, produce them from triangular and tell me what's the expected value of that RFP bit for the actual case, not my modifications. So is that clear? Okay, and I'm floating around if you have questions on anything.
I think the three of us are doing the headlights right now.
No.
Yeah.
You got
100%.
normal, right?
I understand that.
Excellent. How about exponential?
Get that.
So you're in actually really good shape.
Don't believe you.
My last class, we were doing headlights and exponential.
Okay.
But everybody got it, so. My copy.
Yeah, please.
Is this, can I do this for everybody?
Yes, please. Yeah.
And can we go to your Excel?
For sure. With the one from today.
Today. Let's just, let's change this from exponential to triangular. And can you just erase that line? Oh, or maybe copy the sheet would be better, so everybody can see the work.
Oh, I can just delete these?
Yeah. Okay. So now I want to go from uniform to triangular. So that uniform sample.
Yeah.
Let's think about that one. That one is coming out, so his first uniform sample is 0.0691. So it's coming out here, right? So I want to map this, the x-axis, right? So what is the relationship between this curve and this boundary? 0.0691 better equal that, right?
Oh, yeah.
That's exactly what I took.
So that's what's that.
Yes. But in more generality, this guy's is going to change.
Correct.
So it's not always 0.6. I'm just going to call that u.
Okay.
U is my substitute for your value there. But I need x.
Yeah.
So x is u. I'm going to have to do a square root. And that's plus 3.2. So this column should be that.
Okay.
Except, you need an if statement, right? So if U is in some sense small enough,
It's just 0.
no, it's gonna be this guy.
Oh, okay.
And otherwise, it's gonna be, you need to do this same thing for this guy.
I think someone was offered the way you can do the
You mean as in U equals that?
Yes.
Okay.
And what is small enough?
3.2. Minimum, right? So
3.2 is the minimum,
It's just 3.2, like 0.001.
but a uniform is never gonna be above 3.2.
Why not?
A uniform is always between 0 and 1.
Oh, got it.
This is rand, right?
Yeah,
Rand
yeah.
always goes between 0 and 1. So I need an if statement, because it's on this B, I need an if statement on that rand value. I need an if statement on that rand value that tells me, am I using this guy or am I using this guy?
Okay.
So in X world, 5.6 is the problem, right? In rand world, I'm asking you, what is this value that you've already got written down, which is f of 5.6? And that should be number between 0 and 1, and that's the cutoff.
Is the y-axis always
Y-axis is always probability, always. That, I made this, I mean, this is like about as hard as you're gonna get because you've got this king to deal with.
If our ending values in this game that is equal.
Yes. So this says that if my uniform, if my rand is returning something less than this, which you can figure out by that algebra, right? Then my x value had better return something between 3.2 and 5.6. And if my uniform value is returning something up here, f of 5.61, x value is going to return something here. Does that make sense?
Do we need to memorize?
No, I would always give you, you don't memorize anything. No, you don't. You might do not.
How did we get these formulas for what x equals?
Oh, I have to give you this. When I tell you, when the case tells you triangular, the case telling you triangular is defining this.
Okay.
And I just gave you that formula rather than like.
No, I get that.
Is there
What
a
I'm saying is,
Excel
you already have, based on our previous, you already have a savings, right, which utilizes the rest,
This is kind of where I
which basically gives you your.
No, okay, so this one, this is like the baby step between normal and what happens with exponential. And that piece of paper.
Savings doesn't count.
So in your exponential, you've got this curve, right?
Because that is already telling you the
And
exact.
this side is
And what you're trying to do now is to find the exact.
negative x.
It's the other way around, yeah.
I'm telling you that. The lambda was a parameter, so I'm just saying, for the full distribution, not uniform distribution, if I want to allow you to have a family distributions, I can keep that shape, but I can change it. And I'm just saying, if you say lambda equals to 1, so this means the mean is 1, I'm giving you part of the distribution where the mean is 1. And this is the mean now, the P-gap of it is looking like that. So this guy is rounding the area under the curve as I go out this way, and that is generating between 0. Yeah, so this one should always be increasing. So if you think about it, right about 0, the area under the curve is like this. And as I sort of go out, I'm going to be a little bit more. And so this is increasing because this x goes this way, this guy is a little bit more.
You always look like
This is actually not one, this is your key. So this one is around the data.
wait, this is all subtractive.
No, this is, so, how comfortable are you with having this?
It's really like
Can we look at what, you know, on the histogram plots mixed out? In histogram plots, you can do two things, right? You can bins, and if you ask for the cumulative percentage, you get this red line.
right, yeah.
So the red line is like this guy. The bins are like this guy.
But it just
Oh, the bins may or may not be like normal. Exponential bins look like that. But the cumulative percentage, no matter what you see in your bins on Instagram, the cumulative percentage is always going between 0 and 1. So that's exactly the way you do this. Yeah. And for the histogram, you can hear it like the frequency. It's the frequency of occurrence of these different values.
Still trying to do that. It's just starting.
I need this one. I need this one to enact this. And the reason I need this one is because this always needs that mutual verify.
whereas
Correct.
so
So here, you're starting out, this is a couple, these guys are always 2, 0, 1, right? Your first one is like 0.297. So we're starting out wide, you got a brand, what you want to know is what value that translates to. If you know 0.2978 had to equal 1 minus the negative x.
so would it in every number?
Exactly. Exactly.
And so we're just solving for that.
Exactly. But you notice these brands are changing, so in order to do that in generality.
X is equal to something.
Yes. But this is the relationships. So U is like the cell left, the thing that produces the X, the thing that maps in the X is like this. So I need to solve for X. But I have to but I don't have X.
Okay. Alright, so then just take this.
I don't think it's, yeah, yes, you talked about the formula. This is,
I got it.
does that help?
Yeah.
And so this thing that we did here, this, I'm forcing you to solve for non-dot inverse. What I'm doing right here, if this was a normal, you'd be typing in the non-dot inverse of this. And the only thing I'm saying is like this exact same idea works for any sequence. It's just that Excel doesn't always have the command. Yeah? Yeah, yeah. That's the letter. Oh, sorry. Yes, that looks great. Except you're missing some rare roots. Oh, it doesn't look like you went, you have to, it doesn't look like you translated, right? Because here you have that this thing should equal U, right? So that means that U should equal 23. You need that in terms of X. This is your U, you need X in terms of U. So that, yeah. Actually, she just,
Okay.
it's fine.
Okay.
Basically, I didn't know the first one.
Yep.
Figured out the X values that I can get based on these parameters. And then on this, try to put it, multiply this the CDF.
I don't understand.
None of the labels or what I've made it started to be that value. You should, I have, the norm in Why are you done?
Okay. You only do that because you plugged in 5.6 into this bad boy.
Oh,
Okay.
yeah.
A lot of people have done that. I said that because I wanted you to see.
You want us to come to CBS by implementing any X value?
Okay, so I think, maybe I should say this to everybody, because I think, I'm gonna say it to everybody and then I'll come back.
But I'm trying to find the directions and.
Yeah, that's what I should do. Okay, so I know, let me try to get everybody started a little bit, because I think I'm getting a couple similar questions. And, so observation number 1 is, norm dot inverse doesn't apply here. We don't have a normal distribution.
Okay.
But let's relate this to what we were doing with norm dot inverse. Okay? Lost my pencil. So when we were doing norm dot inverse, right, we started over here with a U, and we ended up over here with a norm dot inverse. And I think I need a clean sheet of paper, so let me redo this. This is kind of what things are looking like. Okay, so this looks a little bit cleaner. Okay, so think about it how we did it with norm dot inverse, and you guys were all with me with norm dot inverse. So let's pretend I have a normal for a second. This was a U equals rand, and you came over here and you said, that's the value that gives me that probability, and you said, now I need to map it down to the x-axis. And how did I map it down to the x-axis?
Norm dot inverse.
But for normal. I did that for exponential, for normal. So this was norm dot inverse, and what was my argument? U. So in particular, what I input into this Excel function was U. It was the value that I got back from rand. We good with that? Okay, so the thing that's changed is I have given you a different curve. This curve I have given you, I've given you this curve, and capital F is defining the curve. Oh. Capital F is defining the curve, and what's changed? Excel doesn't have an inverse function for triangular. It does have an inverse function for normal. So what I'm forcing you to do is I'm forcing you to compute what this norm dot inverse does. Why can you do that? So we looked at norm dot inverse. It's this integral of an e to the negative x squared. That's something that you're just not going to be able to compute on your own. Even if I look back to the 1900s before computers, people spent their entire lives compiling tables that gave you what this f function was. Fortunately, we don't have to do that anymore. But I've given you, I'm kind of forcing you to do this stuff. And I'm claiming that I'm giving you a distribution that's easy enough to do that stuff. So let me start it out with a first observation. What is capital F of 5.6? You're looking at the definition of the function right there.
Second one.
Give me a number. Somebody do this calculation for me.
0.25.
It's 0.25.
All day.
Okay.
Oh.
So over here, if I want f of 5.6, this is 0.25. And how did I'm going to move this up for just a second. So f of 5.6, how did you get that? Well, that's a function there, so I just plugged 5.6 into it. 5.6 minus 3.2 squared divided by 23.04. That is the same thing as 1 minus 12.8 minus 5.6 squared divided by 69.12. Either one gives you exactly the same thing. So are we good with this? The function I've given you, this is a probability. This is 5.6. 5.6 maps to 2.5. Good? What does that mean? That means in the case you had a triangular distribution. I'm asking you for what's the probability that that savings is going to be less than or equal to 5.6. What are you going to tell me? 0.25. Okay, so what we've done is for that distribution given to you in the case, I've said, okay, so what's the probability that your savings is going to be less than or equal to 5.6? It's going to be 0.25. What's the probability your savings is going to be greater than or equal to 5.6? 0.75. Great.
Oh.
Now, your uniform, when you type in rand, it could come back down here, and it could come back up here. I'll use an X and an O, like tic-tac-toe. So what happens if your uniform comes in below 0.25? The function changes, right? 0.25 is exactly where that function changes. 0.25 is exactly where the function changes between here and here. And what were we doing? We were doing norm dot inverse. What's the equivalent of norm dot inverse? So let's go down here. Let's say your uniform returns something like 0.1. Okay? So this is your U value. This is something like 0.1. So when you map this back into X world, right? How did I get that 0.1? How did I get that value from rand? So U has to equal this guy, right? So what is that guy? Well, that guy, I wrote it up, so it is x minus 3.2 squared divided by 23.04. So your U is known. Your U is what rand returned. What you need in column C, so your U is your column B. What you need in column C is your X. How did I get to X from this? I solve. Yeah. You're like, okay, that was an obvious answer. I agree. 23.04U. I got to take the square root. I add plus 3.2, and that gives me X. Did I do that right? Yes.
You can assume positive square root.
Yes.
Okay.
Would I want a negative square root? Can I take negative values? No. Okay, so the reason I can assume positive is because I know X is between, the distribution between 3.2 and 12.8. I cannot take negative values. And so the other side might, your rand might also return a value between 0.25 and 1. So what happens if you do that? Well, now you got to go down over here. And what's playing the role of norm dot inverse? Well, it's this guy. So you're going to do the exact same thing we did here, but you have a different equation to solve. Is this methodology clear? So when you type into column C, your column C is giving you an if U is less than or equal to 0.25, you need to return this X value. If U is greater than 0.25, you need to return this X value. And that's giving you your samples from the triangular. There's a little bit to absorb here. So let me step back. Does this help you know what to put in the Excel? Okay, so let me step back. Let me let you, you do this for the next few minutes. And I'm thinking if we can end the class, we're kind of getting samples from a triangular. I'll post my Excel sheet after class, so then we can make sure we're all getting samples from the triangular. We can start next class finishing the case. So right now, let's just make sure we're all getting samples from triangular.
Do we grab the value?
Yeah, maybe do a histogram just to make sure it looks a little triangular.
When you finish it, then.
Yeah.
Can I just look along, because I'm gonna know what that heck is. I can
Okay. And so you have to make it 1 minus that, right? Okay. Wonderful.
Did this help, Sabrina?
So it's like,
Yes.
Stepping all one cell, you're basically
Yeah. And just to make it a little bit simpler, what's U for 3.2? 0. What's U for 12.8? 1. So you really only need to count on 5.6. This is what you're solving.
now you have 3 categories. Basically, you want to basically plot 3.2 to 5.6. And they all have 2 different states minus A corresponding to X equation. And then the second one is where that's like, it could be completely different.
So we can think about it as a limit.
Now you have these partitions. You have
Yeah, I mean, it depends on what I gave you. It's going to be triangular or just PDF, which is how the exponential.
Yeah.
okay, she's given you that's fine. Ideally, you have a value of X. With the condition, calculate the CDF. In this case, my guess is using the CDF. That's what you have.
And that tells you if you increase all that,
So here what happens,
it's still not
your
line to the first I was thinking, just G.
and then calculate the equation. The line for that. So what I meant here is that this is what you already had.
Is it that? I was just making them agree to calculate. So they already knew the but she wanted 2 minutes.
Okay, so keep that highlighted.
I was just doing everything. I know exactly.
But no, it's not your fault, it's like I'm just. Maybe I just, once I see it all filled out, I can just put the pieces together. How are you doing on it?
So it's exactly 4.8, because I think the body did the smallest
Yeah, but
So I like got to 12, but like wasn't done because I thought that was the minimum, and I was just like, wait, no, like I spent way longer than I needed to. Now I need to spend even longer to like finish it. Is that
That's just straight up.
without going way over?
I can even imagine right now because I was
I
feel like at that point I'm talking to a professor like, yo, real talk. It's not what you do. I don't want to write this. I don't want to read this. That's how many pass me.
So even undergrad, I like I 12 pages, but I thought it was like 12 to 14. So I like got to 12 and wasn't finished. Because like worked too hard for something I tried to do. And that's cut it down to
This is gonna get wild.
It makes sense, but
If it's based on,
I don't think the program that focuses on this is going to be recommended. It makes sense to me, but I just don't know. So that's where I'm. It's the same as chocolate chickens. Yeah, I mean, I like it. I don't even know every day. But like, I think yeah. Yeah. I don't
Yeah. First strategy with the global strategy. Yeah. But apparently this class is like all discussion based, which I think, I like those classes.
Okay, so, thank you very much. So what we'll do at the beginning of class on Wednesday is we'll use the inversion method for the triangular to recalculate our Apshot Wednesday, but if you also take a few minutes to sort of go over this in your head. This is probably the conceptually sort of difficult thing, is how do I go from this RAND that Excel is giving me to this observation from this distribution? Thank you. Have a good, thank you. Yes. I'll say, yeah. Oh, no worries, yeah. Thanks.
Deal. Yeah, that's a thing. That's a thing that happens.
People late.
We might as well. Well, we get ourselves in there.
Oh, sure. What do you want?
Yeah. It's sitting there for what? 3 hours?
Yeah.
Pretty good USC's got going on here. Oh boy, oh boy. All right, I'm counting. At least now.